I'm starting the recording.
Okay. Hello. Good afternoon, everybody. My name is Nascimento. I'm a geophysics professor at the Federal University of Rio Grande do Norte in Northeast Brazil, based in very eastern corner of Brazil. And I just want to say thank you very much for Savka and Alex for putting up together this series of seminars. I myself was actually entitled to do this seminar a bit before, I think in the first semester, and I couldn't, but it's good that we are able to do it now before the end of the year. So it's a work I'm going to show today is a commission work we had for the Brazilian Geological Survey. It's basically managed to sort of integrate seismic 2D seismic lines using attributes and meta attributes. And also we did for some time earthquake monitoring from a very sparse network. So the idea is to show today these results. But before I go further, we obviously have some considerations, explain you the situation, the problem, the context, the data that is available. I'm going to show you the seismic network, the 2D seismic lines we used, how we integrated, and how we set up our conclusions, what's basically the message we can take away from this presentation. I hope I can do it in 45 minutes. So we're going to talk about the situation of the area. Is basically Maceió, the capital state of Alagoas. It's based in northeast Brazil. It's a very beautiful scenery that you have there. It's a coastal city and with very warm waters. And it's a big city. Consider a medium-sized city in Brazil. About nearly 1 million people living there. And the word Maceió comes from the former original language from the native people that live in that area all over Brazil. It actually means what covers the swamp. It's a blanket that covers the swamp, because basically I think they were between two areas, a big lake here, and also there's the sea. So the city is sort of halfway through those two water areas. So that's probably because the name comes from this. But anyway, Maceió is a city that it's, as I told you, northeast Brazil. And I'm going to try to show you the chronology of the events. We have on February 15th of February 2018, after a considerably large rainfall, the population start to report. People reported long cracks that damaged road pavements, rainwater channel pipes, and residents. Because of the risk for collapse, at that time, some of the population was affected. That was affected was evacuated. However, on the 3rd of March, which is nearly 3 weeks later, a huge rain, 54 millimeters within 1 hour, occurred in the first hours of the day. Later in the afternoon, people start feeling tremors. That was actually the word that was used by the people. And on the left, I show you the situation of the Google map with the trace that was able to be tracked by the civil defense of the road cracks, cracks on the house, etc., that happened both during the big rain in February and the big rain on March, which culminated with an earthquake, a magnitude 2.4 earthquake on 3rd of March. So that's basically what happened on 3rd of March. We had on the top left, you have the situation map of the Maceió area here. And then you have the location made by one of the seismic station for the Brazilian seismic network. And obviously, we have one single station that basically has a 5-kilometer epicenter area. So that's really preliminary. But anyway, that provoked a huge amount of reports and also investigation from the civil defense and the Brazilian Geological Survey. On the right, you see the mapping of the cracks that was made by the civil defense, and also an explanation of that's also taken from the Geological Survey report that saying already speculated that the cracks formed like a crescent, like a half moon structure on the surface. So that's basically it, yeah. If you don't know, Brazil has a national seismographic network. It's a consortium between 4 universities. It's nearly, nowadays it's nearly 100 broadband stations. And because of the size of the country, it's not possible to have a very close distance to the stations that were recording these 2.4 earthquakes. But obviously, that was reported by the network, and also there was obviously a huge outcry from the public, from the media, social networks, all you can imagine on the situation that was going on, because it provoked cracks on the surface and also considerable damage in many areas. Just for you to have an idea, those are records from 2 stations which are somewhat close to the epicenter area. Unfortunately, this station here, the 3rd one, was not working at the time. But basically, the closest station that we have has a slant distance of 54 kilometers, but the earthquake was felt well over 100 kilometers, and it was actually recorded, over 100 kilometers. That's basically the signature of the events. And if you look at it, some very interesting features for the large amplitude of surface waves. And then the first guess for some people was to say the earthquake was tectonic. Brazil has a low to moderate intraplate tectonism and earthquake activity. On the left here, I show the catalog data since the 18th century, where red you have instrumental earthquakes, and on blue you have historical data. And Maceió is around here, in this area here, near this blue area here. And so the first guess was to say that was tectonic, was people say. But if you look at the right-hand side panel, you see on the right typical magnitude 1.8, 2.4, around the same magnitude of the recorded earthquakes on 3rd of March on the top. And it's a typical tectonic earthquake recorded at the same instrumentation, at the same distance. And on the middle, you have the recording of that 3rd of March earthquake. And you see it's very different from a tectonic event. Yeah, you see there's a huge amount of surface waves. And on the bottom panels on the left, you have the power spectra for velocity records for the event. That's before P wave on the left, and basically showing that the events, all the stations have roughly the same signal, the same noise ratio. And obviously on the right, you have the event spectral signature after the P wave that was marked. And you see that's quite different. We have this long peaking nearly 5 hertz amplitude, which is very clear to see in the signature. So people we immediately, when we saw that, it didn't appear to me as a tectonic earthquake. But anyway, we keep going. And then obviously in the area, there was a considerable damage in houses. This figure here illustrates two snapshots from the most damaged area. This iconic, that house on the right, the pink house, became a kind of iconic example of the kind of damage that was reported at that time. And then you have on the road too, cracks appearing, yeah, very clear, and also damage to the flood and road drains that were in the area too. So the Brazilian Geological Survey, just after, was commissioned by the federal government to check the several hypotheses on the issue that was happening. Yeah? Could it be related to rainwater channel, pipes, etc.? Could be due to rainfall, liquefaction. There were some people arguing on kind of collapsible soils. Other natural causes go for Dolin collapse or either tectonic. Is there people are asking if there was a trigger for the phenomenon to happen? How widespread was it? Some people start raising the question, salt solution mining was something to do with this, or maybe a combination of factors. And on the beginning of 2019, the Brazilian Geological Survey was assigned to investigate the cause, yeah, and also identified that besides that particular area where the pink house was, there were a few other neighborhoods that were also affected. On May 2019, so that's like 6 months later, a bit less than that, there was a public hearing in which the Brazilian Geological Survey concluded the following. It's the free translation from the report, so you can check it. The destabilization of cavities of salt rock extractions occurring, causing halokinesis, salt movement, and creating dynamic situation with reactivation of pre-existing geological structures. Subsidence and ruptile or fragile deformation on the surface in part of the Pinheiro or the areas in Maceió. So basically, Brazilian Geological Survey said that it's a salt-induced seismicity case. And salt industry, salt solution mining, does what it promised in terms of the process of it, basically to extract brine from underground. In the case we are talking here, it's about roughly 1 kilometer depth, and then you inject water and pipe out the brine, and this brine is processed for various chemical use. And over the few decades, more than 30 caverns or 30 mines have been operated in the area. So I show you, it's a PhD thesis from Florencio, from Claudio Florencio, showing the basically the mines, which are these red dots, these black dots here with this purple red ellipses. Some other areas are also exploring, but mostly of the area where it's concentrated, the exploration, is just offshore the Mundaú Lake, which is adjacent to the city. All these areas populated with all urban infrastructure that you can imagine. So there is mining activity in that area. Maceió, in the context in terms of geology, Brazil, it's all this area here is formed by the opening of the Atlantic Ocean, and roughly the geology is a blend of very young geological structures, especially on the coast, with more Precambrian crystalline basement. So if you want to simplify things, you can just put it this way. Yeah, so that's basically crystalline basement, and on the right-hand side in yellowish, you have these Alagoas sedimentary basin. I'm not going through the details of the stratigraphic chart and all the geological history of the setting, because that would take forever. But anyway, it's more complex than that, because when you open the Atlantic, you promote different kinds of faulting which are pre-existing in the area. I show you, and in yellow here is this city, some seismic, vintage seismic line from the National Petroleum Agency, which is open source data, so that you can have it if you want. So basically, if you look at the details from the sub-basin, it's composed of very ramps, depressions, and steps and highs, because of the different, when the time of the opening. And if you look at this seismic shot, seismic line on the right, in the northwest southeast region, which is this seismic line here, or at least toward that strike in which the green arrows point, you see that you have a listric fault, normal fault, and then you have conglomerates and all the sequence that are that's basically the basic setting of the area. A lot of faults caused by the opening of the Atlantic, and sometimes transfer faults too in the area. If you look in more detail now in north, southwest, northeast area, you start to see that the salt that's being explored, it occurs in specifically two areas. One is here near the sea, where I highlight with red the horizontal evaporites, and then the ones that were being explored by the commercially are the Paripuera evaporites. So they are roughly in this more towards the northeast section of the seismic lines. Yeah. So, and they are roughly occurring at 900 up to 1.5 kilometers, roughly. Yeah. And obviously, the thickness of those horizons, of those layers, are not constant. That depends on the position, history, etc. But I show you just an example. There are open source data for that, and I won't bother you, won't bore you with this. But basically, it's sometimes depending. The thickness of the layers can vary from 50 meters of the evaporite layers, salt layers, from 50 meters to a few, sometimes a couple of 100 meters. That's roughly what's been explored there. The Brazilian Geological Survey also concluded with using INSAR data that there is clearly 2016 to 2018. Those were the years that are available in the report. But more interestingly, the red color means basically 2 centimeters. That's velocity for 2 centimeters per year. That's velocity. Yeah. But if you look for profiles of the actual deformation throughout the years, I show you the first one here on red is the Mário Marroquin Street, and then you have how subsidence evolved throughout the various, at least 3 years, 2 or 3 years. And basically you have 40 centimeters subsidence in 2 years. Yeah. And the same happens to another profile that was presented at that report at that time. We even reach up to nearly 0.5 meter subsidence in 2 years. So when they look at the caverns, what's going on there, basically in blue you have the 2015 sonar image, geological modeling from sonar image in the 2015, and in red you have the situation of the mines in 2019, and you can obviously see that the mine is going up. Yeah, and it's actually, I didn't show you the details, is reaching up another top layer which is formed by the conglomerate. And as you know, the conglomerates are not the mechanically more unstable and can lead to collapse. So all this together, they managed to, around the mining areas, they managed to try to map out, firstly, the area of influence of those mining areas and which areas were at risk at first. That was his first work that was done still in 2019, therefore 5 years ago from today. Later, in December 2021, the Brazilian Geological Survey commissioned WEFR and the university where I work to conduct seismic event analysis and process 2D seismic data. So from now on, I move on to actually the work that we did. But I'm afraid it took so long, but it's important for everybody to have this background information in order to understand what's going on. It was 1 year work that we were allowed. And also we had to integrate with structural data, structural geology data, and also we had to organize the database. And one thing that's worth mentioning is the entire network was during the pandemic. And sadly enough, that hindered our possibility to do fieldwork campaigns and also to make maintenance to the seismographic station in a more optimal way, which we couldn't do. But basically, we installed 6 instruments in the area. I know the map showing a bit more. That's because sometimes during some periods we relocated some stations in order to get better data. Was a very challenging environment, as you probably could imagine, because at that time, not the whole area was evacuated. So there was still a lot of traffic. You can see this big stripe here. It's a big road that basically is the main road in which you get into and to get out from the city. And you have the area in between here, which mainly the geology for seismic stations, basically fully consolidated soils. And we had a great help from the civil defense too, including for security of the stations. And on the left, top left here, I show you from the beginning of end of January up to the beginning of December, the time we operated the network. And it's sadly enough, there is a huge amount of gaps. Some stations were able to run for the entire year. Some others just couldn't do it. So yeah, that's what we had. And also looking at the data was complicated because it's a very noisy environment, but we found out that filtering between 1 and 10 hertz, we could pick up the events. But events are sometimes you only have, it's only able to see the S waves in some components, and in some others you just cannot see much. You know, some components that has to do with the probably noise in the cables, but also to the huge attenuation that we have in the area. Sadly, instrument response were not available. It's ongoing work that I'm doing with a PhD student that I have now, trying to recover and try to test in order to have more magnitudes. And all the analysis was made on visual inspection, which leads to, at the end, I'm going to mention that we could improve the interpretation that we have. Because of the time of the monitoring, the urban area, like I mentioned, is still active. On the top panel, I see the number of detected events with UTC time. So you see that the number of events that we detected, as expected, it's inversely proportional to the signal to noise ratio, basically the ratio, the noise, the power spectral density from uncalibrated stations. That was it. Yeah. So that we see that as the day starts, it's huge amount of noise and you cannot see much. The good news here is that probably if I correct one station, I'm going to correct them all because they seem to be the same noise, and probably because the same setup was made between the seismic stations. We got the velocity motor parameters from the seismic and well data. That's basically VP against that. And we could get a glimpse of the seismic events. On the next slide, I show with error bars. So the depth is basically between very shallow depths up to a few events reaching up to 2 kilometers, but very few. But most of them are in between 500 meters to 1.5 kilometers depth from that area. And obviously, when you look at the design of the network that we did on the left with these red ellipses, you see the locations of the network, and I plot the same in the same position the epicenter map. You see that basically because of the poor suboptimal network design, we especially for those events a bit upper on the northwest area, they are poorly located with events basically with error bars over just about 1 kilometer, sometimes a bit more than that, but mostly 1 kilometer error bars. So it was a P wave and S wave picking, and the hypercenter was used for this analysis here. So that's basically the picture that we have from the seismic network. Also in the area, it was commissioned a 2D AWD active seismic survey in the area. There were like 19 2D seismic lines. The most representative lines were those ones which I highlight in red, but there are a few others, but especially for this presentation, I'm going to show results basically from this 117 seismic line, which runs in the northwest southeast direction. But qualitatively, the same happens with these other lines here in the other directions. But because of time, we couldn't do all the lines. The processing was by a specialized company, and the package that was given us was PSTM, pre-stack time migration, and post-stack time migration. A few other versions of the processing, including common reflection surface, which corrects the diffraction points to a curved surface, and that converted for further analysis. We use OpenDetect demo version for this work. Yeah. And because of that, one thing that helped a lot in our interpretation and processing was the availability of wells. That because wells in the area have been drilled for a huge variety of purpose in the mining area, especially exploratory and also lithographic descriptions of well seismic lines. And so we use those information to tie in the interpretation process that was made during the project. Yeah, so you can see that everything is tied in. And the workflow for active 2D seismic data is basically to load up seismic data, well data, choosing which seismic version from that we were available, that were given to us. We basically used time and depth. We didn't go through the CRS corrected image. We use post-stack processing to generate seismic attributes. And then from the seismic attributes, the team interpret the target deflection, the structural fabrics, and the collapsing structures. So I'm going to show you just here. So that's already depth converted, vertical evaluation of just over 2 times, 2 color palettes. And you see from this seismic line, that's the 117 seismic line here. You can see that you can see the layers, and you can actually see some continuity from the top on the surface to the bottom that looks like cracks or some other structure that you have to investigate what it should be. But because of many issues that you have with landed seismic lines like noise, scattering near surface, etc., it's very hard sometimes to directly using just amplitude data to interpret those kind of features. So most of the work was prepared to test different seismic attributes regarding with original, semblance, similarity, and pseudo-relief. And basically, when you do this, sometimes you can actually start to map out a bit more what the actual extent of those layers here, of those structures, those recent structures here. You can see it here, you can see the similarity, but we are not fully happy with this, and we did something which is also very common in the oil industry, especially, was to use seismic meta attribute, which is basically, it's a combo of seismic attributes in order to enhance features. And the one that we found, quite promising one was the amplitudes, a kind of combo with amplitude similarity together with pseudo relief and amplitude, that you can actually start to see very clearly those fracturing from the surface, very shallow layers, up to depth of interest where the seismic events are occurring and the mining is occurring too. So we, for example, in this one, we could see a non-interpret on the left and an interpret seismic line on the right, yeah? And you see the salt very clearly on this magenta or blue kind of horizon. You can see it here, yeah? And you can also map out faults, tectonic faults, which are, guess what, connected to surface too, yeah? You can see that there's a huge connection between what's happening on the surface to, tectonic faults, which are present as inherited from the basin origin, yeah, formation. For example, here I give a zoom from what the work we did was to interpret, and you can see it here, kind of number one here. You see here a kind of, you see that those horizons, they are sort of bent toward the more intense fracturing that's being connected to other fractures, and they go up to the depth where the salt layer are occurring. So basically, there's a direct connections from the fracturing in surface to hypercentral depths or mining depths, which are of interest. So how we did this to integrate, so it was very clear that we had this collapse structure because of the chaotic nature of the sediments. So that was interpreted as a chaotic zone. And we are interpreting this as collapse zones already collapsed from the seismic shots already in 2019. The other thing we did was to get the spatial distribution of well-located events and how those things would map out on the seismic line. was in order to see if we could see any connection between them. And we see that at least for some events, there seems to be correlations, or you might, or at least the events are occurring near the faults, and sometimes up to shallower events. And basically, the idea that we are claiming here is that probably there's because of the hydraulic connection between those structures and on the surface, more towards the surface, and those tectonic faults were active because of this hydraulic connection. And also, that's part of the problem. That's part of the story, because obviously you have seismic events via direct connection to the roof collapse, basically. So it's a kind of couple phenomenon that's happening. So basically, the message to take home: we dedicate our work for imaging using attributes and meta attributes for recent fractures. We were able to see the bulging structures associated to collapsed breccia that we think, and we are inferring there is a hydraulic connection from the surface to great depth, which facilitates the unwanted dissolution of salt layers in the subsurface, causing cave roofs to collapse and reduce the effective normal stress in the pre-existing faults. And both things are promoting seismicity. And seismicity is consistent with faults associated with direct subsidence and pre-existing faults. And collapse earthquakes are possible at the time. That was the conclusion, since these structures are compatible with seismic interpretation that we did. Yeah, it's an ongoing work. We have still a lot to do with the integration of geophysical observable that's freely available through the geological survey. We, from our seismological perspective, have to improve the event detection using more. There's a whole bunch of tools that you can use to detect event and then estimate magnitude and improve seismic location, with obviously consequence to the interpretation that we are presently giving. I just want to say big thanks to a whole bunch of people. I was brave enough to name those people because there's always the risk that you forget someone. Yeah, so the people that were basically most involved during the elaboration, doing the work in this period that I'm presenting you right now. Okay, and that's it. I think I've managed to make it, Safka. You're not going to be